Welcome to one more lecture of our course on fundamentals and biomedical application of quantum science. Today I'm going to give you another type of topic, and we've been speaking about wave function, things like this all the time. Can we actually see by eye the evidence of quantum mechanics? Can we actually see the wave function somehow or some aspect of it? And the answer is yes. And because today is the last lecture of our course, I'm going to explain to you a topic that's very much in fashion, which is going to the quantum mechanics on the macroscopic sense, trying to produce physical system that we actually can see by naked eye, the quantum mechanics. And that somehow is going to give you a feeling what's going on in these topics in different sense. Okay, so I'm going to speak about cooling and trapping atoms for you, and the production of what we call Bose-Einstein condensation, which is actually a way to look to the quantum system by naked eye. But to do that, we have to get closer to the absolute zero of temperature with the matter. And the reason for that is normally when we have a physical system, it turns out that being in some finite temperature, what we have is we have a many, as you know, finite temperature means we have to have a distribution of energy. Temperature means energy. And in the atomic level or molecular level. And depends on that temperature. We have many levels that are occupied, and therefore it's very hard to see actually the wave function. Because to really see the wave function, we must somehow put many particles in the same quantum level. If we are able to do that, we are able to see it. Because, if we put atoms inside a balloon, we know that they are there, normally. But in the deep inside, they are like de Broglie waves, but so short that we can't see, because to see, we have to see the quantum effect. So we should produce the de Broglie wavelength to be as large as the size of the container. And to reach macroscopic size, de Broglie wave length, we need to go down in temperature, right? Okay, so we're going to give an illustration of this so you believe even more in quantum mechanics. Some people thought that all this was abstract mathematical tools for explaining the system. That's in the past. Now, people believe in the wave function even more, because it is really fantastic that the distribution of mass obeys the wave function square, the way I told you, or the distribution of charge. And that's what I'm going to show to you in this lecture. It is a final lecture, so it's like we're going a little bit for you to see the advance of quantum mechanics in the present days in seeing macroscopic effect of quantum mechanics. And by the way, each time that quantum mechanics manifests itself on the macroscopic level, we find super properties of the matter, like superconductivity, right? Is not the only one we see. We see also superfluidity. We see what we call the quantum Hall effect, that I am going to take the liberty to say super Hall effect, and so on. And there are many other super properties that we don't know, and we have to understand well to be able to apply them. Like superconductivity is already beginning their applications, and superfluidity will find the application very soon. Is already many propositions of applications. Okay, so this lecture then will be a little different, and I'm going to start to explain to you why to see things on the macroscopic level, we have to go to lower temperature. And we have to go to lower temperature because, as I told you, temperature is related to energy that is related to momentum. And we can relate to this is de Broglie. We can relate to the de Broglie wavelength with this momentum, still h divided by the momentum, but because of temperature, normally the momentum is given by this. You see, it's a root square of 2 pi the mass times kT. K is the Boltzmann constant. So if we have a macroscopic system, and if we go down in temperature, means that the wavelength is growing, you know, until we reach the situation where the de Broglie wavelength, that normally I like to call quantum dimension, becomes compatible to the size of your system. In that situation, you cannot rely on classical mechanics anymore. So if I have a balloon or a box where I put a gas and I cool down, normally you can imagine that the gas is a uniform distribution everywhere, as we learn, you know, ballistic motion of particles and everything. But if we go down, that picture breaks down. If we go down in temperature, we reach a situation where the de Broglie wavelength is on the order of the size of this container. And therefore, we cannot think about atoms moving ballistically to produce the property of the gas. What's happened there is that we reach the quantum situation. And then the system change behavior. It manifests the wave function. The wave function is spread all around the space available. And then we can see, we can observe. Right? Okay, so let me give you a few hints how we do that. And this is, we could say that is the physics or chemistry of low temperatures. And as we go down, we evolve in the understanding physics. You know, normally when we are here in hundreds of Kelvin, we have the traditional chemistry going on. And this is the de Broglie wavelength. I know it is very small scale, but I will tell you. This is 1 Bohr radius, right? This is 100 Bohr radius. This is 1,000 Bohr radius, and this is 1,000,000 Bohr radius, right? And the de Broglie wavelength here then is shown here as nanometers, and this is the range where we have the atom. So everything that's quantum is inside the atom, and then we start to see the quantum manifest in different things as we come to other region. And then when we come to 1,000,000 millimeter type, you know, hundreds of microns, we get on the macroscopic size. And then there are many phenomena going on as the temperature goes down. The de Broglie wavelength, as I showed to you, which is the quantum dimension, it's also coming down, going up, I'm sorry. And we pass. You know, when we reach liquid helium is already a very important, is about 1 Kelvin. That showed to us the presence of superfluidity. And then we go down and down and down, and until we reach situation where we are from many microns to fraction of millimeters of size. And then when this Bose-Einstein condensation takes place, which is nothing more. What is Bose-Einstein condensation? It is nothing more than the manifestation of the quantum mechanics on the macroscopic level to us by occupying a single quantum level. And then this is techniques to come down with temperature. And to reach so low temperature, which means nanokelvin, you cannot do that by putting in a refrigerator. You have to do a special thing. And that's what I'm going to explain to you how we do. Well, normally temperature is associated with the energy. This is what we call the kinetic interpretation of temperature. And if we look at any gas around, there is a big distribution of velocities. And normally we associate the distribution with this temperature, right? And then we can measure this in different ways. Since the temperature is related to momentum, if we somehow can measure the momentum transfer, we can actually get the distribution and we can get the temperature. Now, to start to put this down, we have to use a very interesting quantum mechanic properties of light. I told you that the light has the photon, and I told you the photon has energy. But nothing is more relativistic than light, and the energy that we can see is actually c times the momentum. And then I have another expression here for the rest mass. But the photon has no rest mass. But because the photon has energy, it has also momentum. And the momentum of the photon is the energy it carries divided by the velocity of light. And we told you that this is h times omega. H times omega divided by h bar, divided by h bar omega divided by c is the momentum the photon carries. So when a photon interacts with an atom, it gives a kick. It's not only energy that is transferred, it's momentum is transferred. And as you know, if a momentum is transferred to the atom, we can make a force on the atom, right? And this is called the radiation force. And the radiation force is a very important concept because imagine I have a beam of atoms coming in this direction. So the beam of atoms is coming this direction here. Then what I do? I shine photon opposite to the motion. Photon is coming that way. Oops, it's not very visible here, huh? Photon is coming opposite. It turns out that each photon that's absorbed can produce a kick, a recoil on the atom, and slowly I slow down the atom. I start with atom that's very fast, typically 1,000 meters per second, and I slow down to centimeters per second. That's a way to start to remove velocity. That's a way to start to remove momentum and to produce large wavelength. And then there is a nice situation that gives the Nobel Prize to Stephen Chu. Oh, this technique of slow down atoms gave the Nobel Prize to William Phillips, right, from NIST. And then Stephen Chu came with a very nice idea. And the idea is the following. Imagine you have an atom. The atom is moving. I will shine a light that way, and I shine another light that way. If the atom has zero velocity, it sees equally both beams. But if the atom has velocity, we will have a Doppler effect, right? And velocity somewhere. And the Doppler effect shifts the light for the atom. It's the Doppler effect, right? If I'm moving towards the light, I see the photon bluer than really is. And if I'm going further from the source, I see the photon red shift. So then Stephen Chu said, oh, if I have an atom that's moving and I put two laser beams red shifted, this atom will be more resonant to this beam than to that. And then we will slow down until it stops and then maybe became to move a little bit around. So what Stephen should demonstrate was that you were able to make a viscous force, a damping force for the atoms, and then you can remove the energy efficiently. And if you put photons, if you put laser beams coming to many directions, actually you can produce a very efficient remotion of energy from the atom. And then they were able to demonstrate, because if the atoms are slow, they hang around. So if you have a vapor and you turn on this what we call optical molasses, you see a bright spot on the center because the atoms there are moving very slowly. Well, and then comes another very smart guy, David Pritchard, and said, well, let's now use the internal structure of the atoms. Remember, I told you the electron has a spin, and in the presence of magnetic field, the spins can go up and down, or if there is zero spin, does not modify. So David Pritchard imagined ways of putting light with different polarization because the selection rules. And then he made not only a molasses, he made not only a way to remove energy from the atoms, but also to confine the atoms. So by putting coils, by playing with the internal structure, you are able to confine the atoms and make them to be in a very low temperature. Very low temperature. And once they are in the very low temperature, they don't move a lot. So this is a glass cell where we make all this I told you. And what you see is a bright spot of atoms basically on the millikelvin of temperature. Those are atoms in millikelvin. Millikelvin, is millionesims of Kelvin. Well, once the atoms are there, and I want to produce a kind of confinement to see the wave function, right? We turn on magnetic field, and we produce what they call magnetic trap. Again, because the atoms are like tiny little magnets, the energy grows with the applied field. Remember I explained this to you when we explained the nuclear magnetic resonance. Therefore, if I'm making in space a kind of magnetic field, I confine the atoms. So I produce a kind of parabolic field. And this parabolic field allows my atoms to be confined in a very low temperature. And what we learn in quantum mechanics, if I have a potential like this, holding the atoms, there is a ground state energy here. Somewhere here, there is a ground state. If I make all the atoms to be in this energy, I will produce a giant wave function where all the atoms has the same wave function. So I could observe, because instead of being spread around in this potential, you can imagine like a box, but this is a harmonic oscillator type. We call a harmonic trap. If I make all the atoms to be in this energy, I can see a giant wave function, and then I can take a picture of it. So this was done. People put in here, they start where? They start with what they call this Magneto optical trap, which produce atoms to microkelvin of temperature. Microkelvin, are millionesims of Kelvin. And then they start with this little ball of atoms. Then I turn on the magnetic field around. So I produce a box, a harmonic box, around the atoms. And then I turn off the light. Turn off the light. Turn off the light and wait. And do some extra steps to cool down even further the atom. How I do that? I do by evaporation. I come here and wait the atoms, because here is like a hill for the atoms to go up. I wait the atoms to come to the top, and I kick them out. When I kick an atom out, I'm taking together the energy of the system, and the rest of it thermalizes and comes down. And this is what has been done. People has done that, and then they reach a situation where the energy we reach, the kT of energy, is around the energy of the ground state, on the order. Of course, it's not exactly, but doesn't matter. And in this case, all the atoms has to be in the ground state of energy. And if they are in the ground state of energy, they must not more be a ballistic motion. They must have a giant wave function. And this giant wave function can be seen because this is macroscopic. This is a confinement that has many, many microns on dimension. And with microns we can see, with a very good magnifier, we can see those atoms. And this was done. This was done in very nice experiment. And what they really observe. They observe that when they slow down, and they reach a situation where the de Broglie wavelength is on the order of the size of the ground state of your system. Before they saw all the atoms spread, this is the profile of density. But suddenly a peak appears here, as you can see. And this peak, as you can see even clearer when I go down, is the wave function square of the ground state of those atoms. So, and how I observe this? I do an optical absorption. I send light to it, and I observe. And I observe, and I measure the temperature. I know the temperature is compatible to my confinement. And then I produce this macroscopic build-up wave function with all the atoms occupying the same wave function. And that's called Bose-Einstein condensation. So what is the Bose-Einstein condensation? It's when all the atoms occupy a single quantum level, and then all the properties of the system will change, because normally I have the contribution of so many levels. So many different energies are contributing to the system. And here I come with all the atoms in the same quantum level giving the same contribution to the system. So everything changes. Heat capacity of the gas, pressure on the walls, viscosity, because now there is no this ballistic motion of collision that creates the viscosity, and the atoms, there are many, some more complicated mechanisms, but the atoms, they stay there without viscosity. They do not needs energy to flow. And that's a change of behavior. And in physics, when we have a change of behavior, we call a change of phase. In this case, we go from the classical gas, where it's all spread around the confinement, to a very well-behaved peak. All the atoms behave exactly the same, with the same wave function, all in the same level. And then that's a mapping of the wave function square, because the wave function square is the density of charge, or the density of mass in here. And that I'm mapping the density of particles, the density of particles on the space, which is a picture of the real wave function square. There are other parts of physics where we have equivalent things. And one of the things we have is the laser. The laser is when we put all the photons on the quantum sense to have the same wave function. So they all behave the same. Normally I have light, I have portions of light going everywhere. But then I make all the photons going exactly the same way, and I have the laser. This means that all the photons have the same wave function. Now I do the same with a gas. And this experiment were done in many different atoms, rubidium, sodium, lithium, and many others so far. And each time we do, we learn to understand even better the quantum behavior of this system. You see, here is the wave function of the atom as a whole, because the atom is a particle like the electron. And now I'm looking the wave function of the atom itself, confined in this potential. Of course, I'm not seeing the phase of the wave function, I'm seeing the amplitude square, but still, it's a good gain. So, you know, the classical gas go to a quantum gas the same way that the normal light goes to the laser. So the Bose-Einstein condensation is making to the atoms exactly what a cavity with gain is doing to the light, making the laser. So having the Bose condensate is putting all the atoms in the same wave function. Having a laser is exactly putting all the photons in the same wave function. Once I have that, I can do wonderful physics with this, because now I have a quantum system that I can see. And I can study properties of the system. Right? I can measure the temperature. How we measure the temperature in the nanokelvin? We cannot stick a thermometer there. Normally what we do is we have the atoms in the potential, confined. We liberate. And then, of course, they're going to expand. Like when you have a balloon and you blow it, the gas expands. And we will expand, and I follow the expansion with time. I look the size of the cloud growing, and then I observe how fast it goes. I can get the temperature. I get the temperature by looking the rate of expansion. And then I can see the change in behavior of those systems. And I can take a picture and I can get the overall properties of my system. Okay, so how the system looks like in a cartoon looks more or less like this, where we see the potential. We somehow remove the fast atoms by lowering the potential, and then finally we have the atoms in the condensate. And if we look at the wave function, right, the wave function looks like this. What I have is a thermal gas. Suddenly a peak starts to appear on the thermal gas, and then I make all the atoms to go. That is a temperature where this happened, because it's related to de Broglie wavelength. So by changing the de Broglie wavelength, by changing the temperature, I make all the atoms to go in the same quantum state. And then if I look at the density on the center, I see a changing behavior, and then I can calculate the wave function and see that this jump is proportional to the root square of the number that characterizes exactly the wave function that's there. There is a temperature where this happens. There is a real transition. So we say that there is a critical temperature. So normally I have a broad distribution when I'm above the critical temperature. And then suddenly what's happened? The wave function appears and became more or less a pure condensate. And that is a picture of the wave function square, right? And then I can understand all the quantum properties of the system. But there is another kind of phenomena that we can observe on this, because I told you about the Heisenberg principle, remember? And I told you that when we squeeze the quantum particles, whatever has less space available it gets more momentum. I told you this. Okay, let's see the expansion, evolution of a Bose condensate. Let's start with a Bose condensate. Well, this Bose condensate has a shape that looks like this. It is squeezed in this direction. If I let this expand, I told you there will be a manifestation of the momentum. Whatever has more momentum will expand. Right? So, what do you think is going to happen? The system is going to expand faster where it's more squeezed or is lower? Of course, because this is more squeezed, it has more momentum. Therefore, after a while of expansion, I see the opposite. I see the system expanding faster on the direction that was born squeezed. And this is a proof of this quantum system. So this is a gas that's fully quantum and obeys all the quantum principle. So this is a real observation of the uncertain principle by eyes, right? Because of the uncertain principle that we learn, x times p is on the order of h bar. Whatever I have this smaller, I have this bigger to be able to reach this situation. And that's what's happened. This dimension here was the smaller dimension before the expansion. So it was this. And this big dimension, of course, they don't decrease. I did not put in scale here because here is much bigger, right? This should be this big, more or less. Just to be, and this is the axis and everything, but we put it in perspective here, in only not scale. If you do that in a gas that's not quantum, you don't observe that. What you observe is going to isotropic expansion. The things expand isotropically. So this Bose condensation is a way to see by eye the real quantum mechanics in action. So everything is very real, right? And we should not suspect of that. The Bose condensation, which is a way to identify macroscopic quantum properties, has many, many applications. You know, and as you already realize that each time we evolve the understanding of quantum mechanics, we evolve all the fields of science, right? Because everything at the end of the day is quantum, and we needed to consider that. And Bose condensates is a nice way to evolve the understanding of the quantum mechanics, especially when there are many, many particles together. We call this the physics of many body, because this is what it is, nature, and that's what we have to learn. And that has wonderful contribution to atomic physics, to understand lasers in general, as I told you, to do magnetism, to do statistical mechanics, to do fluid mechanics, you know, superfluid, to do condensed matter, to do field theory, you know, these things of suddenly all the atoms go to a single quantum state, is what they call spontaneous breaking of symmetry. It gets an order factor on the system. Because it is a superfluid, I can understand how to make vortices on it, and then I can produce turbulence, which is a kind of thing I do for a living as well. So, this is a nice quantum system that helps us to evolve all the understanding of quantum mechanics in general, quantum mechanics of a system that is made of many, many atoms, many, many particles. As I told you, we came to the end of our course. It was a wonderful trip. I start by give you the fundamentals of what we know on classical mechanics, which is motion, which is the oscillatory part of the electromagnetic wave, and then I explain to you how that should be better understood based on the observations of nature, based on phenomena that can only be explained if we introduce a different concept for the behavior of the mass, for the behavior of the particle that has mass. And then we could understand this parallel between electromagnetism, which is waves of, in the wave interpretation, with the waves of matter. And then we had a master equation that help us to understand any situation. I may not know how to solve the Schrödinger equation, but if I know how to solve, I get better understanding on the phenomena going on. And nature is quantum, deep inside everything in nature is quantum phenomena going on. And to really understand and evolve the applications we have, we needed to know concepts of quantum mechanics, and that was the main idea, the main goal, the main aim of this course, is transmit to you concepts of quantum mechanics and give some applications so you could insert yourself in the quantum contest. Okay, well, I hope for you was a pleasure, and for me it was a great pleasure to be able to give you those ideas. Of course, this is just the principles, the fundamentals. If you like the topic, there are so many things to do on the understanding of biomedical effects or biological effect in general using quantum concepts. There is a full open field of opportunities. Okay, my name is Vanderlei Bagnato, and together with this nice cooperation with the Hagler Institute in the Texas A&M University and the University of São Paulo, we were able to provide you with this course. See you in the next opportunity. Bye-bye.